In this video, we'll discuss how to count the number of significant figures in a measurement. Measurements can be described in terms of accuracy and precision. Accuracy is how close to the correct value the measurement is, or the amount of error that occurred, and precision is the level of exactness of that measurement, and it's related to the uncertainty of the tool. In these four examples, we can describe the result in terms of accuracy and precision. In A, we didn't hit the bullseye, low accuracy. We didn't get the exact results, they're not clustered, so we have low precision. B, we didn't hit the bullseye, low accuracy, but we got a cluster here, which means we have a certain level of exactness. We were able to replicate our results, so that's high precision. C, no bullseye, no cluster, low accuracy, low precision. D, we hit the bullseye, high accuracy, and we had the same results, high precision. Measurements with an analog instrument will include the known digits plus one estimated digit. And in this case, we got 21.6. We could have said 21.5, but we could not have said 21.55 because that would be two estimated digits. Sometimes you don't get that estimated digit. For example, this voltmeter right here, the needle is so wide that you don't get that estimate. So we just have to stick with what the instrument says, and that's 0.15 volts. Now, when you're comparing the precision of two different instruments, notice that A is 4.8, B is 4.71. We have an extra place value because of the level of precision of this instrument. So which one's more precise? Well, B is more precise because it has more tick marks and we can read it to a higher place value. Also, it has more significant figures. And significant figures are the digits in the actual measurement. And what we have to do is look at zeros. Zeros can be part of the measurement, but they can also be just a placeholder. If it's part of the measurement, it's significant. If it's just a placeholder, it's not significant. So how do we identify if it's significant or not? We use the rules. Any number that is not zero is always significant. Zeros can be significant if they are between significant figures, sandwich zeros. Leading zeros are not significant. Trailing zeros can be significant only if there's a decimal in that number. So look at this example. Leading zeros, not significant. Non-zeros, significant. Sandwich zeros, significant. Zeros to the right, or we call them trailing zeros, they are significant because there's a decimal in this number. Now, when you make a measurement, you're basically saying two things. This is the value of that measurement, and based on the number of significant figures, you're explaining how reliable it is. So more significant figures equals more precision or more reliability. So counting significant figures, there's a trick. If there's a decimal present, we count digits from the Pacific side or from left to right, but we have to start at our first non-zero digit. If the decimal is absent, we count from the Atlantic side, and we do the same thing. We go from right to left, counting at our first non-zero. Example, decimal, Pacific side, count left to right. 1, 2, 3, 4, 5. Decimals present, count from the Pacific side, left to right. We start at our first non-zero, 1, 2, 3. Scientific notation, we only count the coefficient. Decimals present, 1, 2, 3. No decimal, count from the Atlantic side. At our first non-zero, 1, 2, 3. Decimals present, skip these zeros, 1, 2, 3, 4. Scientific notation, we only care about the coefficient. Decimals present, we count from left to right, 1, 2, 3, 4. Decimals absent, starting at our first non-zero, 1, 2. Decimals absent, starting at our first non-zero, 1, 2. Decimals present, 1, 2, 3. Decimals present, 1, 2, 3. Okay, hopefully that helps.